Okay, we are back with part 2. So we want to prove the following. We want to prove now, so that's Cantor's proof actually. Cantor's proof that reals are uncountable. So there are more reals than we can count, differently stated. This is saying that it is impossible to establish a one-to-one correspondence between reals and counting numbers. So we cannot really pair them up, pair every counting number with every real number and have nothing left unpaired. So this is what we're saying. We're further saying that the infinity of reals is larger than the infinity of counting numbers. So in part 1, obviously we saw one type of cardinality, and that cardinality is of the same cardinality as the set of counting numbers, integers, rational numbers. They are of the same cardinality. Sometimes is known as Aleph null cardinality. Anyway, so before I actually proceed with the proof, just a little observation here. Let's say that you are given two numbers. So you are given two numbers, and all digits of these two numbers, except one of them, are hidden from view. So let's say I have a number here, and then the decimal point, and then 3, and then decimal point, decimal point, decimal point, decimal. I mean, not decimal point, but digit, 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 and I don't know what these digits are. So I have some other number here, decimal point, 5, decimal point, decimal point, decimal point, decimal point. Looks like both numbers have the same number of digits in their decimal expansion and otherwise. I mean, they have the same number of digits. So question is, are these numbers same? Could this number be the same, or they for sure are different? So that is the question. Okay, could these two numbers possibly be the same? The answer is no, because even if these other digits that are hidden from view were identical, the first digit after the decimal point of this number is 3, and the first digit after the decimal point of this other number is 5. So no matter what the rest of them are, since these two digits are not the same, these two numbers cannot possibly be the same number. And this is at the heart of the argument, this little observation. So let's see. All right, so we're going to show that to show that reals are uncountable, we are going to prove that the set of all real numbers from 0 to 1 is uncountable, and that is the same actually as saying that the entire set of real numbers actually is uncountable. So it'll suffice, it will suffice to show that the set of real numbers from 0 to 1 in the interval 0 to 1 is uncountable. Okay, so I will give some simplified version of this with somewhat of an actual example. So let's see. Proof. Let's say that, so I claim that I have a list, I will write down an infinite list of real numbers, And my claim is that the listing is complete in a sense that I have written all possible real numbers and I will attempt to count them. Okay, so let's say I have a list of reals here, some random real numbers, 0, 5, 5, 6, 2, 7, 3, 6, 8. The next number is 0.02, 593, and so on. The next number is 0.612, 3598. The next number is 0. This is completely random, by the way. There is no pattern here. I'm just trying to write an infinite list of real numbers, and my claim is that, or the claim is that we cannot possibly, the list cannot possibly be a complete one, in a sense that there will be more reals than we can actually count, because once we claim we have a complete list of real numbers, then I can put them in a one-to-one correspondence with counting numbers. And if I have more reals than I can count, meaning if I have more reals than counting numbers, then I've proven that reals are uncountable. Okay, so it doesn't really matter that the list could be a completely random list with numbers from 0 to 1, which I claim is complete, or we claim is complete, and we want to show that it cannot possibly be complete. Alright, so where am I? So the next number is 0. Let's say 0.0083786 and so on. Then I have some other numbers, 0.84722222, and so on. And then some other number, maybe 8395838139856, and so on. Okay, so let's say that I have infinitely many of those. All right, so let me assume that the list is complete, and I want to arrive at some sort of contradiction, and the contradiction will be that the list cannot possibly be complete. When I say complete, again, I mean in a sense that is countable. I can pair everything in that list with counting numbers. So here are the counting numbers. So I pair this number with number 1. So I call this the first number on my list, the second number on my list, the third number on my list. That means I'm pairing that with counting number 3. The fourth number on my list, the fifth, the sixth, the seventh, and so on, and so on. And here I have some real number is paired with number n, and so on. Okay, so now we consider the following. Now we consider, again, I'm not writing it, but I'm saying it. The claim is that the list is complete in a sense that I can count things here. Meaning I have in this list as many numbers as I have counting numbers. Okay? And I want to show that that cannot possibly be the case. So what do we want to show? How are we going to show that? We are going to produce some real number, some other real number that for sure is not going to show up in this list that I claim is complete. So that's the game plan. So we are now going to consider the real number m. Rather, we are going to construct this number. should say construct the real number m. Well, how are we going to construct this number? So number m will be some number again between 0 and 1. So let's say that number m will start with 0 point something. So now I'm going to decide on the digits next to the decimal point, and those will be infinitely many because my list here is infinite, and I'm going to decide on these question marks according to this list. In what way? Okay, so let's say that the question mark will be either number 2 or number 4. Well, the claim here is that there's nothing special about number 2 and number 4. You can use any other number, with exception to number 9, and then I'll talk about it in a bit. But again, I repeat, there's nothing special about 2 and 4. You can use 3 and 7, you can use 1 and 6, you can use any 2 digits you like, you can use blocks of digits here. So instead of just writing this x and y, much like the book does, I thought it's a much better idea if I give some actual numbers, and we'll see how the argument works with this list, or any list for that matter. 2 and 4 are not special in any way. There is no particular reason for me choosing 2 and 4. Just I chose them. Okay, so how am I going to decide on this question mark? Which of this will be 2 and which of this will be 4? But I'm going to construct this number, of course, with infinitely many 2's and 4's in its decimal expansion, and that will be a real number, obviously. So here's the rule. The rule for question mark. If the nth digit after the decimal point of the nth number in the list of reals, of the nth number in the list of reals is 2, then the nth question mark, is a 4. Otherwise, the nth question mark is a 2. Well, what does that mean? So I repeat, this number m will be made of 2's and 4's in the decimal expansion. How will I decide which is which? So this is what we're saying. If to decide on the first question mark, so for example, to decide on the first question mark, meaning the first digit after the decimal point in m, we look at the first digit after the decimal point of the first number in our list of reals. Okay, so number m is 0 point. I want to decide on what the first question mark is. To decide on this question mark, I should look at the first digit after the decimal point of the first number. Okay? I will look at it. If this is saying if this number is a 2, then this will not be a 2, but it will be a 4. It will be a 4. Okay? So number 5, first digit after the decimal point of the first number is a 5. It's not a 2. So if it's not a 2, then my first question mark is a 2, according to this. If the first digit after the decimal point of the first number in the list of reals is 2, then the first question mark is a 4. Otherwise, the first question mark is a 2. Looking at the first digit, this first digit is a 5, it's not a 2. So if this is not a 2, my first question mark will be a 2. Okay, to decide on the next question mark, I look at the second number after the decimal point of the second number on the list here. So the second digit after the decimal point of the second number on the list of reals. Okay, so I'm looking at it. If this is a 2, then this will be a 4. If this is not a 2, then this will be a 2. But this is a 2, so according to the rule, the next digit will be a 4. To decide on the third question mark, or the third digit after the decimal point of this number, I should look at the third digit after the decimal point of the third number, the third real number on our list. That is a 2. So that is still a 2, which means that my third question mark will be a 4. I'm moving on to the fourth one. To decide on the fourth one, I have to look at the fourth digit after the decimal point of the fourth number in the list. Okay, that is still is a 2. So I make sure I make this a 4. To decide on the fifth, I look at the fifth digit of the fifth number. So 1, 2, 3, 4, 5. Looking at this, this is a 3. This is not a 2. So if this is not a 2, then this will be a 2. Moving to the next one, so the sixth. 1, 2, 3, 4, 5, 6. The sixth here is a 2, which means that this will be a 4. The seventh, 1, 2, 3, 4, 5, 6, 7. The seventh here is 8, is not a 2. If it's not a 2, then the eighth here is a 2. And so on. And so on. So now question is, is M in our list of reals? Meaning, is it possible for this number to actually appear somewhere in this list? The answer is no, because we are making sure that is not. How are we not making sure? We're constructing a real number that is unlike the first. Why it is unlike the first? Because no matter what the rest of the digits of these are, and no matter what the rest of the digits of these are, their first digits after the decimal point, we're making sure are different. So no matter what these two numbers are, they cannot possibly be the same number, because the first digit after the decimal point on both numbers is not the same. We're making sure of this by imposing this rule. Okay, could number M be the second in our list? No, again for the same reason. Because the second digit after the decimal point of this number and this number are different. We made sure of it. And so on. Cannot be like the third, cannot be like the fourth, cannot be like the fifth, the sixth, the seventh, the nth, and so on. So, we're making sure that by constructing this real number, we're constructing this real number in such a way that it is different from absolutely every real number that I have on this list. So, but I've claimed here that I have all the numbers in the list. I mean, this is some arbitrary list of real numbers between 0 and 1. Yet number m is a real number that for sure does not show here. That means that I have more reals than I can count. So if I claimed before that here's a complete list of reals that I could count, I found another one that surely is not in my list. So there are more reals than I can count. Okay, so m does not appear in the list. Since we're making sure that m is different by a digit from all numbers in the list, all numbers in the list of reals. In the list of reals that we're counting. So this argument, how did we make sure that it's different? By imposing this rule. So this argument works for absolutely any arbitrary list that you can pick. Your list may be very different looking from my list, but if you impose a rule like this, no matter what number you come up with, it's for sure that that number will not be on your list no matter what list you create. So from all numbers in the list of reals that we're counting, therefore there are more reals than we can count. Okay? That's the same as saying that reals are uncountable, or the infinity of reals is larger than the infinity of counting numbers. So these two infinities are of a different cardinality. Okay, so this otherwise is known as the diagonal proof of Cantor's theorem, because the argument sort of moves diagonally. Now, a couple of comments, and this is actually for you to think about as homework. So, think about. What if the number m that I'm constructing, I decided that it is 0.5 and then question mark, and then you'll decide on the question mark exactly the same way as we did here. Could this m be on the list? So that's for you to answer, but I'm going to give you a hint. Whenever you decide on the question marks here on the digits of m, to decide on the first, you go look at the first number on the list. To decide on the second, you look at the second number here. To decide on the third, you look at the third number here, and so on. Number 5 here is already decided for you, meaning that your number will look something like 0.5, and then the rest of them will be 2s and 4s. Is there a possibility that the number will be on the list? Since 5 is here already and is the first digit after the decimal point, to decide on the second, you're immediately going to jump on the second number on the list. You are going to ignore the first. I guess that's the answer, but think about it some more. So this is one thing. Another comment. As I said before, number 2 and number 4 are not special in any way. You could use other numbers with exception of number 9. Why? If you use, for example, 2 and 9, you might have your number m may be something like 0.2929999 with 9's never ending. But 0.2999 with 9's never ending can also be written as 0.3. And 0.3 may actually show here as 0.3 has a different decimal expansion, a different looking decimal expansion. That would be 0.30000. But 0.3000 and 0.2999 are exactly the same number. So you might run into problems should you decide to use number 9 as one of those choices. Exactly for the same reason as I mentioned before, that 0.99 is in fact the same as number 1. So your homework also would be to provide with a scenario where using 2 and 9 would actually not work. So provide a scenario, meaning use not the same list, some other list, but instead of 2 and 4, use 2 and 9, and show that this argument will not work if you have 2 and 9. Okay, so provide a scenario where using for the question mark 2 and 9 would not work. Would not work. Okay, and having said all that, this will be end of lecture 13. Until next time, everyone.